Alright, welcome back to another video by Firestarter Graphics and Engineering. Today we're going to discuss the linear rod example for a 3D printer to see if the beams, I don't want to use the word beam, sorry, the rods that I purchased, how much they're going to deflect with a 3-pound glass bed and aluminum plate across 4 bearings, how much that's going to deflect on those, because remember it spans 500 millimeters, it's a huge print bed, so there could be some deflection. I don't know, that's what I want to find out. Okay, so there's multiple ways to tackle this. When I first learned how to do this, I tried it all in 3D, but apparently, I don't want to use the word but apparently, there is a way you can do it one-dimensionally, and it's really crazy that you can do these things in one dimension and it works out. I mean, I guess it works because the math that we use for like back of the envelope or napkin maths equations, just to test things. You can use online beam calculators and whatnot. And speaking of that, I used an online beam calculator to solve this problem, and it gave me zero point 0.3 millimeters of deflection, and I thought that was way too much, which it is. But you'll see using FEA that it's not that much. It's actually like 50 microns, if that. It's very small deflection. Um, so back of the math envelope, back of the envelope math is good for a rough starting point. So I even verified my math with an online calculator, and it got the same number. And so I don't know what's different, and it's kind of bugging me. Let's see if I have that actually still. Okay, so I went ahead and found it's, what is it, calcs.com, free tools analysis, and it's the free beam calculator. This is what I just used. I think this is important to go over a little bit. Length of the beam is 500 millimeters. I'm using 210,000 for my Young's modulus. The area of cross section, I don't remember what that is, but let's see. We can figure this out real quick. Okay, I went ahead and calculated the area of a circle. It's 50.27 millimeters squared. Second moment of inertia, the I. There's an equation for this. I don't have it off the top of my head, so let me go find it. Okay, I went ahead and calculated it. There's an equation for it, and I got 201.6. Okay, so now we have our properties. We know it's going to be pinned at position 0 and 5. I want it like that, but what other? We could do fixed. We should try fixed and see what happens instead of just pinned. And then we're going to go to the simple loads, and we're going to delete this row. I want a distributed load. I'm going to call this bearing 1. And let's see, its magnitude. I've got to remember its magnitude here. Well, first its start location is at 210 millimeters, and its end location is 230. And this one I'm going to start at, I don't know, 290 and end it at 310. And then let's find a start magnitude because I need 0.75 pounds in kilonewtons per meter. So let me calculate that real quick. Okay, doing the conversion, it's actually 0.16 kilonewtons per meter. It's an odd number. This is going to be bearing 2. Okay. And the start magnitude is going to be the same. And the same. Okay. So, if we look down here now, it's calculated everything on the right hand side. We have this, our shear moment diagram and our loads here. Everything. Deflection. Okay, it's actually, yeah, quite small. So 0.09, that's not bad at all. Now, here's what's interesting. If I went ahead and put these as just pinned, you'll see how much that drastically changes now. See the negative 0.3 millimeters? So it all depends on the type of support that you use. On a 3D printer, we want it to be fixed. So that's where my math went wrong, is I used pinned instead of fixed, which doesn't allow for rotation or any movement, which we're getting, like, what is that? 0.09 millimeters, so roughly 90 microns. So let's do this in FEA and see what we get. So I just wanted to show you this. This is a very handy tool to use. So give me a second to set up FreeCAD and we'll get going. So just bear with me. Thank you guys. Okay, I went ahead and opened up FreeCAD. So let's just do this first one-dimensional example. So I'm going to go ahead and hit parametric part. Every parametric part starts with a sketch. We're going to do this on the XZ plane, and we're going to start with a line. And I want this line to be 210 millimeters in length and 0 degrees. That automatically constrains it. Okay, that's my first length. Now this is where the bearing comes into play, and I know my bearings are 20 millimeters in length and it's still straight. Okay, then I'm going to have a 40 millimeter gap between the two at 0 degrees, and then I'm going to have another 20 millimeter and 0 degrees. That's for my bearing. That's my second bearing. So that's 80 right here, 80 millimeters, 210, and then the last one should be 210, 0 as well. So if we look at this, it should all be centered. So this is how my bearing plate works on my 3D printer bed. So the bearings are 20 millimeters in length, 8 millimeters in diameter for that rod to go through. So this is what it's going to look like at center point. Alright, I'm going to go ahead and hit close. Now, we're not going to do anything special right now. We're not going to pad it. We're not going to put a circle right here and extrude it or anything. We're just going to leave it like this. Now we're going to switch to FEM and watch the magic happen. Okay, so as per use case, every FEM needs an analysis container and everything needs a material. I'm working with Steel G200. We're going to hit OK. I'm going to double check to make sure the material property is loaded. Okay, 210, that matches what we have. Poisson's ratio, everything okay. Perfect. Now, the analysis needs constraints. So I'm going to pick this. I'm going to hit add. We're going to click this point here. Click that point there. We're going to hit OK. Now you'll notice everything is upside down, but that's alright. If we just click bottom, whoops, one more. We're going to click the left side so we can kind of look at it from this way, because you can't really orientate these little feet. You can if you draw lines a certain way. You could put them, you could do other things, but there's no need. We're working with up and down, so direction doesn't matter. We just need to pay attention to our sign, just like free body diagrams. Okay, so next we need a load, and we know that it's 3.36 newtons across each bearing. So I'm going to hit add. We're going to click this line. We're going to click that line. Notice it's pulling down. That's what we want. I'm going to hit OK. Okay, we are almost done. The last thing, actually there's two things we need to do. So the second to last thing is we need to add some sort of 1D geometry cross section, because in order to do any type of beam calculation, it needs a cross section. Notice in here it needed a area cross section, so we're going to add the same thing to here. So we're going to click that, and we're going to go from rectangular to circular, and it's 8 millimeter diameter. That's all you got to do. Then you can hit OK, and then it's going to do the same math. It's going to do very similar math, but across an entire meshed one-dimensional. But what's funny, this is considered one-dimensional. All the math in this is one-dimensional. It's not. There's no matrix maths. There's no X, Y, and Z. No, nothing. This is all one-dimensional. So let's compare it. Okay, so next click the body. I'm actually going to click the sketch instead. I'm going to do Gmesh, and I guess I'll just apply. No, let's do 1 millimeter and then half. Let's hit apply. This should only take zero point 0.1 second. Hit OK. So now we have a mesh. Now we need to drop the solver, double click it, write the IMP file, run calculix, and it should only take half a second. Okay, we're good. So now all of a sudden you're like, whoa, hey, what's this? It added a rod for us. See, nice circular rod. How about that? But we're going to hide the pipeline, and we're going to double click the results. First I'm going to get there. Double click the results. You can see a mesh, kind of. Yes. Okay. And we're going to do displacement in Z, and it says its max is 50 microns, and our back of the envelope math was 90 microns. So not bad. I mean, let's see what it looks like. Yeah. So, you know, not bad at all. Look at that. Nice and purty. So if you want to hide, let's hide the forces. Now you can kind of see what's going on. There we go. So we can close this now, and we can go up here, hide the body. Let's go back to the pipeline. Let's double click it, and let's move it to von Mises. And now you can see where all the stress concentrations are. So 1D element. So now why did we get a difference there? So they're both one-dimensional, but here's the thing. Once we added that mesh, it drew a mesh along that entire line in one-dimensional, and now it has become this huge matrix equation using a lot of trigonometry and a lot of matrix math to solve for all these forces. So it's a little bit more accurate. So it's still technically 1D because we're not dealing with any 3D objects or XY, I mean, other directions, but it's still matrix math. And so pretty good. And you'll see that when we do the next method here in the next video, it will be a similar, probably only 1 micron difference when we do it in 3D. So anyways, I just wanted to show you guys how to do that in FreeCAD, one-dimensional. It's kind of nifty. I mean, that's not a lot of deflection. I'm still debating if I want to do this because I was going to do it to make my printer high-speed printer, but since I'm still rocking Marlin 1.1, I don't have linear advance or pressure advance, so I'd have to update my firmware, which I really don't want to do, or use a Raspberry Pi or a small laptop and run Clipper and run it that way, but I really don't want to mess with things. I could save, I don't know, 75 bucks from buying all the parts and actually put that 75 bucks to a brand new printer that's high speed. Anyways, that's my opinion on what I'm going to do. I have no idea what I'm going to do. Anyways, I hope you guys enjoyed this video. Next will be the 3D case of this. So thank you for watching. I just love all the pretty colors. Holy crap. So does my wife. I just think that's so cool. I just like looking at the pictures. It's cool. Anyways, thanks guys. Talk to you later.